Alright students, we're still talking about logarithms, and now we're going to talk about logarithmic differentiation. Now before we get into taking the derivative using the logarithm, we need to talk a little bit or review a little bit on the properties of logarithms. Now this again is something that hopefully you remember from actually college algebra or maybe pre-cal or maybe trig. But some of these properties, of course, we're going to use and use repeatedly. So let me list these properties real quickly, and then we'll do some basic examples applying them. Okay, the first property we need to discuss here is the fact that when you have a product, like you have the natural log of x times y, you could rewrite this as the natural log of x plus the natural log of y. Now when this was presented to you in college algebra, they didn't use the natural log, they used just the logarithm, which is a log base 10 instead of a log base e. So if you had the logarithm of a times b, we said this was log of a plus log of b. So you can apply all the logarithmic properties also to the natural logarithms, which we're going to see in this section. So another one of these properties would be if you had the natural log of x over y, you could rewrite this as the natural log of x minus the natural log of y. Another property that we use repeatedly is if you have the natural log of x to an exponent, say of r, you can pull the exponent in front of the natural logarithm. Now we use that a lot. Now some other basic properties that we use are to remember that the natural log of 1 equals 0. That's something we use quite a bit. And the natural log of e to the x equals x. So those are some basic properties that we will use off and on as we're using logarithms to differentiate. Now some real basic examples of applying these properties before we use it in differentiation, so we can again be really comfortable with this. So to apply the properties now to some basic examples, again not differentiation yet, then it would be something like this. Suppose we had the natural log of 5 cosine of x. Now that's a product between 5 and cosine of x, so we could rewrite this as the natural log of 5 plus the natural log of cosine of x, using that first property. Now if we had a quotient like the natural log of x plus 1 over 2x minus 3, we could rewrite that as the natural log of x plus 1 minus the natural log of 2x minus 3. Another example would be if we had the natural log of 1/8. We could rewrite that as the natural log of 1 minus the natural log of 8. Well, the natural log of 1 is 0, so this just turns out to equal the negative natural log of 8. Okay, another example would be something like the natural log of 4 to the power of x. We would pull the x in front of the natural logarithm and rewrite this as x natural log of 4. So those are looking at the properties and applying those properties. So now let's take a look at what the title of this section is, which is actually logarithmic differentiation. So part A was just kind of a review of using the logarithmic properties. So part B is actually going to some examples to understand what they're wanting us to do when they want us to use logarithmic differentiation. Alright, and some of these examples can be kind of lengthy, but let this be part B, and these are examples. And the question will say, use logarithmic differentiation. So that's how you know that they want you to use this process. Use logarithmic differentiation to find the derivative. So be sure you look closely at the question. Logarithmic differentiation. That's what we're doing here. Okay, so suppose we have example 1. where it says y equals the square root of x times x plus 1. Now, sometimes it's hard to take the derivative, and so we use logarithms to take the derivative. So this time we're going to use this logarithmic differentiation to take the derivative of this. So what that means is we begin by just taking the natural log of each side of this equation. Alright, so now I'm going to go ahead and using logarithms, I'm going to rewrite the right-hand side using those properties. So this is the natural log of x times x plus 1, all to the 1/2 power. Well, that last property said you can bring the exponent out front, which we just did. And now when you have a product, we can rewrite this as the natural log of x plus the natural log of x plus 1. And then if I distribute this, and you get pretty quick at this, but if I distribute this, this is 1/2 the natural log of x plus 1/2 the natural log of x plus 1. Okay, so bring your natural log of y down from the left side. Now we're ready to differentiate. Okay, so to differentiate this is going to become on the left side implicit differentiation. The derivative of natural log of y is 1 over y times the derivative of y. On the right side of the equation, we have 1 over half, and the derivative of natural log of x is 1 over x times the derivative of x. And this one is, the derivative is 1/2 x times the derivative of the natural log of x over 1 is 1 over x plus 1 times the derivative of x plus 1, which is x. So now I have, I wonder if I can scroll and still see this. I think so, okay. So now what I have is 1 over y times y prime equaling what? 1 over 2x plus 1 over 2 times x plus 1. So to solve it for y prime, this is y prime equals y times this 1 over 2x plus 1 over 2. I guess we just write that 2x plus 2. And the last thing we need to do is replace y with what it really equaled, which was the square root of x times x plus 1 times 1 over 2x plus 1 over 2x plus 2. And there it is. There's your first derivative using logarithmic differentiation. Okay, let's try another example. Same thing, different example. Suppose we have y equals x times the square root of x squared plus 1 over x plus 1 cubed. Okay, kind of ugly. So we're going to use logarithmic differentiation. That's really what the directions said to do, so we will do this. So the first thing we do is we take the natural log of each side. So the natural log of y equals the natural log of this rational expression. And I'm going to change this to x squared plus 1 to the 1/2 power over x plus 1 cubed. Take the natural log of the whole thing. Okay, so let's apply all those properties that we know. So this is the natural log of the numerator minus the natural log of the denominator. Oops, that's a 1. Okay. Now the first one is a product, so this is the natural log of x plus the natural log of x squared plus 1 to the 1/2 minus the natural log of x plus 1 cubed. So another property now is to pull these exponents in front of the logarithm. So this becomes the natural log of x plus 1/2 the natural log of x squared plus 1 minus 3 the natural log of x plus 1. Okay, and the left-hand side is natural log of y. Notice we have not taken the derivative yet. We have just rewritten this so that it will be easier now to take the derivative. So now I take the derivative. So the derivative of the natural log of y is 1 over y, y prime. The derivative of the natural log of x is 1 over x times the derivative of x. This would be 1/2 the derivative of the natural log of x squared plus 1 is 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x, minus 3 times the derivative of the natural log over x plus 1 is 1 over x plus 1, and the derivative of x is 1. So we have a mess, but it's actually a pretty easy algebraic expression. So this is 1 over x plus 1 over, what, 2x squared plus 2 minus 3 over x plus 1. So now to solve it for y prime, I multiply the right side times y. And remember, I'm just going to replace y with its value from the original question for my resultant answer. So last but not least, y prime is y from the original question. Scroll up here. I can see it in my written notes. Up, 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 up. Okay, this is y. So I'm going to put this in place of y. Whoa. Here we go. So this y was the original question, which was x times the square root of x squared plus 1 over x plus 1 cubed times 1 over x plus 1 over 2x squared plus 2 minus 3 over x plus 1. There it is. So you can use logarithms to differentiate when you have a really complex, expression to work with. So if you're good at those properties, then this is a nice way to differentiate. So I'm going to stop the recording here, and I still have to do integration of logarithms to complete this section.